This is the third presentation in the series about inclined plane, in which I will present solutions to two similar and interrelated questions. It is highly recommended that you watch these presentations in the right sequence because this third part is a little bit advanced. So to understand this stuff, you should first watch at least presentation number 1 and ideally both of them. So this time the question is slightly different. What minimum force do you need to exert onto the object to prevent it from sliding down the ramp? So this situation is a bit different. I will switch now to the pen mode. And we'll start from drawing a inclined plane. There is some object on this plane, but this time we have a person here, and okay, this is the head. Here are, sorry, here are the legs. Alright, so not bad. We have this person pushing, of course, upwards, okay, up the hill, because you need to push it upwards in order to prevent from sliding down. As previously, we have a gravitational force pointing down, and this gravitational force can be decomposed into the sliding force and the normal force. We'll have the friction force, which I will not show here, but also for everyone who watched the two previous episodes of this series, it should be quite obvious by now. It comes as I keep repeating, as a no-brainer. We start with these three formulas: the sliding force mg sine alpha. Why is that? Check in the first presentation in the series. So sliding force is the force that tries to slide this object down. Normal force is this force. This is the pressure of the objects towards the inclined plane. And we also have friction, which is fmg cosine alpha, which is pointing, normally pointing upwards. I will change the color to green, which is how I usually draw, friction. So this is the friction. And now the point is that preventing an object from sliding down means basically keeping this object motionless, okay, keeping it in place. Without any additional action from this man here, from this person, it may be a woman, okay, so from the person, okay, we need to balance the forces that are acting on this object. Without balancing, you can see that sliding force, at least this is how I drawn these forces in the diagram. The sliding force will not be entirely balanced by the friction, so the object will be slowly going down with surprise probably an acceleration of 4.13 meters per second square. Again, if you want to know why or how I know this, watch the previous parts of this video. Okay, so what happens here is that this guy or girl, okay, the person on this slide needs to exert a force, okay, and let's call it perhaps a f x. Okay. Of course, this force has to be the force exerted or acting upwards. Okay. And the basic maths behind it is that our net force, which is, and again, if you don't know why, you should check the previous parts of this presentation. The net force is sliding force less friction force, and this is mg sine alpha minus f cosine alpha. Basically, for the balancing condition of the situation is that the net force of just the object, so sliding force minus friction force, minus fx should be equal to 0. 0 means that it will not slide down, it will not go up. Okay, f minus fx equals 0. So the minimum force that we are looking for, minimum force, fx equals f equals this thing, mg sine alpha minus f cosine alpha. And this this question, which started to look quite tricky, quite funny, in fact is much simpler than the previous two exercises I presented, because we can now put the values to the formula. M, we now know the mass of this object. It's quite massive, 100 kilograms. Okay, times G, it's now not shown here. Yeah, it's not shown here, but G is typically 10. Okay, so I will add here additional data that you will get during the in-class tests. Okay, G is 10 meters per second square, sine 30 degrees is 0.5, cosine 30 degrees is 0.87. Okay, so we have mg times sine alpha is 0.5 minus 0.1, this is the coefficient of friction, this one, multiplied by cosine alpha is 0.87. So our fx equals to 1000 times 0.5 minus, okay, sorry, I have no idea what has just happened. Okay, 0.5 minus 0.087, so this is 1000 times 0.413. This is 413 newtons. Newton is the unit of force. What this solution means, this is the minimum force you need to exert on the object to prevent it from sliding down the ramp. 413 newtons, is it huge or not so huge? Okay, it's quite a lot, but 413 newtons is the force that you need if you would need to pull up an object which would have roughly 41 kilograms. Okay, so it's like pushing 41 kilograms. It's not not a lot. Okay, not a lot. It's just a fraction of the original mass of 100 kilograms. This is the minimum force, because if this guy would exert any stronger force, of course, this relation here would start look differently. Fx would be stronger. Okay, would be stronger. and at some moment this guy, or this person, would push the object forward up the hill, okay, or wouldn't. Here is the fourth practice question in the inclined plane, and it looks very much similar to the previous one. What minimum force do you need to exert onto the object to keep it moving up the ramp with constant speed? The only difference is that now we want to keep it moving up the ramp instead of prevent of sliding force. You might think that any force higher than whatever we found in the previous question, it was 413 newtons, whatever higher than that would be enough. We'll find it out. Okay, so this question is really very similar to the previous one, so I have the same additional data for the calculations, and I will also reuse my picture that I prepared previously. So we have the same person pushing the same object up the slope. So Fx, the blue force, is again the force exerted by this person to balance the net force that would otherwise cause the object, the crate or whatever it is, would make it slide down the ramp. What else? We need these forces to balance, because the question says to keep it moving up with constant speed. And from the first law of motion, we remember that constant speed is achieved by an object in the isolated system on which there is no force that would be acting, or all forces are balanced. So if this is the constant speed, this means that forces are balanced. Our so-called no-brainer part, it's a sliding force, normal force, friction force, and I have copied and pasted the calculation of the net force from the previous exercise, previous question. Is it correct? Net force, it's sliding force minus friction force. It looks all familiar. Of course, the force exerted by the person upwards should balance this net force ideally, and if we continued the calculations in this way, we would inevitably get 413 newtons as in the previous question. But if this question looks like your old friend, the previous question, my warning is it's a false friend. Look at this friction force here. Okay, this friction force, the small green arrow, was drawn previously to show the friction force that would happen if the crate was sliding down the ramp. When the friction force would try to prevent this motion, so it would be acting upwards. But now we have a totally different situation. Okay, we have a person pushing the object up the ramp, so there's no more any reason for this friction force acting upwards or forward. If it was, it would be helping this person, okay, and we know that friction always prevents the actual motion. So the positioning of this green arrow is wrong, and it should be like this. Okay, friction, when you push upwards, the friction will always try to prevent you from pushing upwards, so it will act downwards. And you can now see that both the sliding force here and the friction force, the green arrow, they both act in the same direction, and this means that my net force formula which was based on friction preventing the sliding motion, is wrong. It's not anymore acting. It is not anymore acting like this. So I'm switching to the pen mode, and I will do the absolutely necessary amendment. Now the friction force is helping, this is a plus, okay, friction force is helping the sliding force and adding on top of the forces that prevent this person from pushing the object upwards. So now to push it upwards you need to not only balance the sliding force but additionally overcome whatever friction we have here. I will now switch the color to black to write the formula for Fx. This is this blue force exerted by the person. It has to be balanced with the net force, okay? Or you could want to express it as Fx minus F equals 0, whatever, the condition of balancing. Whatever we have, Fx equals Fs plus Ff, so it's mg sine alpha plus F cosine alpha. So our Fx equals now 100, that's the mass, times 10, the gravitational acceleration, multiplied by 0.5 plus 0.1, it's still friction coefficient, multiplied by 0.87 cosine of our inclination angle. So this is 1000 multiplied by 0.5 plus 0.087. So this is 1000 multiplied by 0.587, and this is 587 newtons. This result is significantly different from the result in the previous question. Okay, 587. The previous one was here 413. So what really happens if you are standing here and trying to push the block of the cart up the hill, but you are too weak to exert this minimum force to prevent this from the sliding down, so you push it with anything lower than 413 newtons. Okay, the object is sliding down because you cannot prevent the sliding down, it crushes you and you die. If you push it with at least 413 newtons, but you don't exceed 587 newtons, what happens is that this is the range in which you can increase your force. You of course prevent it from the sliding, but your force is not yet sufficient to start moving up. And only when you achieve the force 587 newtons, you will start very slowly, initially with a constant speed, pushing it forward, pushing it up. And of course with a stronger force, this movement will be accelerated faster and faster. This concludes the series of presentations about solving questions in inclined plane. I wish you all possible successes in the in-class test, and just please remember there will be one more type of a question about ballistics for which you can find a separate recording. Thank you very much.